This question is about slip at the maximum torque in a V by F induction motor drive. In an induction motor, in speed control we have studied that V by F, this is constant flux method. When V by F is constant, voltage and frequency are varied such that V by F is constant, and this is a method of speed control. So in this method, the slip at maximum torque, there are four statements about slip at maximum torque. The first statement is the slip at maximum torque is directly proportional to synchronous speed. The second statement is it remains constant with respect to synchronous speed. Basically, we have to find out the relationship between SMT, slip of maximum torque, and synchronous speed. Okay. So in general, in induction motor, slip corresponding to maximum torque is R2 divided by X2, where R2 is per phase rotor resistance, R2 is per phase rotor resistance, and X2 is per phase rotor reactance, per phase rotor reactance, per phase rotor reactance at standstill. This is important to write. X2 is reactance when rotor is standstill. So this is the formula for slip corresponding to maximum torque. Okay. Now X2 is reactance of rotor winding, and X2 will be omega into inductance of rotor winding, where omega is angular frequency with which voltage is generated in the rotor winding. This will be 2 pi f into L, and f is the frequency with which voltage is generated in rotor winding. So the frequency at which voltage is generated in rotor winding, this is called slip frequency. But X2 is defined at standstill. So if rotor is at standstill, let's say this is rotor winding. If it is at a standstill and field rotates with synchronous speed, and which is directly proportional to frequency of the supply. Okay, and if rotor is at a standstill, the relative speed between the field and rotor winding will be synchronous speed, or omega s. So the voltage generated in the rotor winding when rotor is at a standstill, the frequency of the generated voltage will be, the slip frequency will be supply frequency when rotor is at standstill. So X2 is nothing but 2 pi f, where f is supply frequency, into L. Or we can say that X2 is directly proportional to supply frequency. So SMT, R2 is a constant, R2 has nothing to do with the supply frequency. So we can say that SMT is inversely proportional to X2, and X2 is directly proportional to supply frequency. So SMT is directly proportional to supply frequency. SMT is directly proportional to 1 by supply frequency, or SMT is inversely proportional to frequency. Now synchronous speed is, this is directly proportional to frequency, so SMT will again be inversely proportional to synchronous speed. Okay, so in V by F control, frequency is varied, supply frequency is varied, accordingly synchronous speed will vary, and accordingly rotor reactance at a standstill will vary. So the slip corresponding to maximum torque, this will have inverse relation with the synchronous speed. At any arbitrary speed of induction motor, let's say the speed is Nr, synchronous speed is Ns, the frequency of the generated voltage in rotor winding will be slip frequency, that is S into supply frequency. Okay, in this case the actual reactance offered by the rotor reactance at S slip, this will be 2 pi SF into L. 2 pi F into L is X2, rotor reactance at standstill. So actual reactance offered by the rotor winding at any slip S, this will be S into reactance offered by at standstill. But here in this formula, SMT is R2 divided by X2, not SMT is not equal to R2 divided by actual rotor reactance. Okay. Here we have a 4-pole lap connected separately excited DC motor. The connection is, the armature winding is connected in lap, we have lap connection in the armature winding. So in case of lap winding, the number of parallel path is equal to number of pole, that is 4. So we have 4 number of parallel path and it delivers 40 ampere current. Okay, we have 4 parallel paths. Let's say these are the voltages generated in each parallel path, and it delivers a constant current of 40 ampere to the load. Okay, so current generated in each winding or in each parallel path will be 10 ampere. Okay, current generated in each parallel path will be 10 ampere. Okay, the total load current is number of parallel path into the current generated in one parallel path, and the total voltage will be voltage generated in one conductor into the number of conductor connected in series. Okay, so we have this kind of DC motor and it is running at 600 rpm. The speed is 600 rpm. It means the speed will be, in 1 minute it rotates 600 times. So in 1 second it will rotate 10 times, or in one rotation, for 10 rotation it takes 1 second time. So in one rotation it will take 1 by 10 second. This is 100 millisecond. Okay, we have 4-pole DC machine. Let us draw it. Okay, let's say these are the 4 poles. This is north pole. In machine we have studied that the poles has to be alternately south pole and north pole. There cannot be consecutive 2 north pole or 2 south poles. So if this is north pole, this will be south, this is north, and this is south. And let's say this is armature frame, and let's say these are armature conductors. These armature conductors are, first these are connected to ring, and voltage is collected on the brushes. Okay, so in one rotation it takes 100 millisecond time. It means, let's say this conductor, this will rotate and it will again come to the same position after 100 millisecond. What will be the time taken by this conductor? Let's say this conductor is in the completely influence of north pole. So what will be the time taken by this conductor to get into the complete influence of south pole? If this conductor moves in the influence of south pole, this is 1/4 rotation. Okay, so in one complete rotation it takes 100 millisecond. So in 1/4 rotation it will take 100 by 4, 25 millisecond. So that's why the time 25 millisecond is mentioned here. Or we can also say that there are 4 poles and each conductor at any time, each conductor will be in the influence of out of these 4 poles. There are 4 poles and it takes 100 millisecond in one complete rotation. So to touch all the poles it takes 100 millisecond. So we can say that for 25 millisecond a conductor will be in the influence of a single pole. Let's say this is the conductor and it is in the influence of north pole. So for 25 millisecond this conductor will be in the influence of this north pole only. A DC machine or a DC generator provides constant current 40 ampere to the load, but we know that the voltage generated in conductor is always AC. Okay, the voltage generated in the conductor is AC, but in DC machine with the help of commutator and brushes this AC voltage is rectified to DC voltage. So let us consider these 4 conductors and let's say these 4 conductors are in the influence of this north pole. So in each conductor, and let's say these 4 conductors are connected in series. Okay, the voltage generated in each conductor will have different magnitude, but if these 4 conductors are connected in series, the total voltage will be the arithmetic summation of the voltage generated in the 4 conductor, and the summation of voltage generated in each conductor will be this voltage V. Okay, but if these conductors are connected in series, the current in each conductor will be 10 ampere. This 10 ampere has to be constant. Okay, so the current in each conductor will be 10 ampere, but voltage generated in each conductor will be different, because let's say this conductor is completely influenced with the north pole, so voltage generated in this conductor will be maximum and voltage generated in this conductor will be somewhat less than voltage generated in this conductor, but current in each conductor will be same because these are connected in series. Now after rotation, when these 4 conductors will come in the influence of south pole, when these 4 conductor will come in the influence of south pole, obviously the polarity of voltage generated, this will be reversed, and now these conductor will generate current. The current generated in these conductors will be in opposite direction. So let's say in this position the current is 10 ampere, so in this position current will be minus 10 ampere. Okay, although while moving from this position to in the position of south pole, the current in each conductor will be reversed, but with the help of commutator and brushes the direction of output current will be same as 10 ampere. But we are asked about the current in armature winding, armature conductor, not the output current. So our current in armature conductor will be 10 ampere, let's say for north pole, and after 25 millisecond these 4 conductor will come in the influence of south pole. So for south pole the current will be in opposite direction. So C option will be correct. For more detail, you can refer the theory lecture of DC machine. There I have explained that why the current in all these 4 conductor will be constant at 10 ampere and how voltage will be generated. Okay, and how this voltage will be constant. This voltage will not be exactly constant. The shape of the voltage will be like this. It will vary a little bit at 10 volt. So for more detail you can refer the theory lecture of DC machine. These are the two windings of an ideal transformer, and in the load a pure inductance is connected. The pure inductance L is connected here. We have to find out the equivalent inductance at port 1. This inductance is connected at port 2. Okay. So in the transformer, let's say we have a source connected here, B, and reactance X is connected here. When you will refer it to the primary side, the turn ratio is given as n is to 1. Okay. Here the ratio is n is to 1. Okay. So when you will refer this reactance to the primary side, this will be V, and this reactance will be n by 1 square into x. This is n square x. Okay, where x is omega into L. Okay, so here x equivalent is n square into x. This is n square omega into L. So x equivalent is omega n square L, or x equivalent can be represented as omega into L equivalent. Now if you will compare, we will get L equivalent is equal to n square into inductance. So inductance will increase according to the turn ratio. If at the place of inductance, if we had capacitance here, let's say we have a capacitance here, then what will happen in case of capacitance? When you will refer this side, x equivalent will be n square into x. X equivalent or reactance will always increase according to the turn ratio. But x is inversely proportional to C. X equivalent is also inversely proportional to C equivalent. Xe can be written as 1 by omega C equivalent. This will be n square into 1 by omega C. So 1 by omega C equivalent is 1 by omega C by n square. Omega is cancelled. Ce will be n square. So if you have an inductance here, equivalent inductance will be n square times. But if you have a capacitance here, equivalent capacitance will be divided by n square. The reason is the reactance is inversely proportional to C. But in case of inductance, reactance is directly proportional to inductance. In a transformer, this is 400 volt 50 hertz transformer, has an iron loss of 5000 watt at rated condition. Rated condition means the voltage is 400 volt. This is the meaning of rated condition. So in this condition, loss is, the iron loss is nothing but summation of hysteresis loss and eddy current loss. This is 5000 watt at 200 volt and 25 hertz. Hysteresis loss plus eddy current loss is equal to 2000 watt. And we have to find out, when this transformer is operated at 416 volt and 52 hertz, we have to find out the ratio of hysteresis loss divided by eddy current loss. Hysteresis loss divided by eddy current loss. Okay, so the conditions are given in terms of voltage and frequency. So we know that in terms of voltage and frequency, the hysteresis loss is directly proportional to V square divided by F. In the theory lecture, first we defined relation of hysteresis loss in terms of flux and frequency and flux, and then we converted it into in terms of voltage and frequency. Okay, and the eddy current loss is directly proportional to V square. Okay. when we will talk about torque in terms of voltage and frequency. Okay, so let's say in first condition, or we have to find out hysteresis loss divided by eddy current loss. So PH by PE will be, we can say that PH is directly proportional to V square divided by F, and PE is directly proportional to V square. So we can say that PH by PE will be directly proportional to V square divided by F divided by V square. This is cancelled. So the quantity we have to find out is directly proportional to 1 by frequency. Okay. So what we have to do, we have frequency here. In all these three cases we have frequency. So if you have ratio of PE and PH in first condition, you have frequency here, you have frequency here. So if you know the ratio in first condition, we can find out the ratio in third condition also. So to find out ratio, we need to calculate the exact value of PH and PE. We have two equations here. Let's say in first condition, the hysteresis loss is PH and eddy current loss is PE. This is equal to 5000. In the second condition, for second condition, what will be PH? In second condition, PH will be, voltage is halved. Okay, PH is directly proportional to V square, so PH will be V divided by 2 whole square. PH will be directly proportional to V divided by 2 whole square divided by, frequency is also halved. So at the place of F, we will have F by 2. And in first condition, PH will be directly proportional to, let's say this is voltage, V square by F. And in second condition, PH will be directly proportional to V by 2 whole square divided by F by 2. This will be V square by 2F. Now if you will compare the two hysteresis loss, you will find that in the second case, hysteresis loss is 50% of the first hysteresis loss. So in first condition, if you have hysteresis loss PH, in the second condition, the hysteresis loss will be PH by 2. Plus, now similarly we can conclude for eddy current loss. In the first condition, eddy current loss is PE, which is directly proportional to V square. In the second condition, voltage is halved, so PE will be directly proportional to V by 2 whole square. So PE is directly proportional to V square by 4. Here PE is kV square and here PE is kV square by 4. So in the second condition, the hysteresis loss is 1 by 4 times of first eddy current loss. This is eddy current loss, by mistake if I said hysteresis loss. So in the second condition, hysteresis loss is 1 by 4 times of, in the second condition, eddy current loss is 1 by 4 times of eddy current loss in first condition. And the total loss in second condition is 2000 watt. Okay, this is equation 1, and if you will solve it, you will get 2pH plus PE is equal to 8000. This is second equation second. If you will solve these two equations, you will get PH equal to 3000 watt and PE equal to 2000 watt. And what is pH? pH is hysteresis loss of first condition. Okay, hysteresis loss of first condition, and PE is also eddy current loss of first condition. So what is pH by PE here? pH by PE is 1.5, and initially we concluded that the quantity pH by PE is inversely proportional to frequency. Okay, So PH by PE is 1.5 at which frequency? When frequency is equal to 50 Hz. And we have to find out PH by PE at f equal to 52 Hz. And we have this information, PH by PE is inversely proportional to f. Okay, so you have increased frequency here and this is inversely proportional to frequency. So PH by PE in the third case, this will be PH by PE in third case divided by PH by PE in first case will be equal to frequency in first case divided by frequency in third case. Since we have inverse relation, so 3 by 1 will be 1 by 3. If we had direct relation, we would have 3 by 1 equal to 3 by 1. So PH by PE in third case will be PH by PE in first case into F1 by F3. So PH by PE in first case is 1.5 into F1 by F3, 50 divided by 52. This will give you 1.44. If you find this method of finding PH by PE, if you find this method difficult, you can also do one thing. To find out exact value of hysteresis loss and eddy current loss for the third case, and then you can get the ratio. We have a DC shunt generator. So first let us draw the circuit diagram of DC shunt generator. Let's say this is the terminal of DC generator. This is armature. This is armature resistance is 0.01 ohm. And since this is shunt DC generator, so field winding will be connected in shunt with the terminal. Okay. Since this is a generator, so the direction of current will be out of the machine. This is armature current, this will be load current, this is terminal voltage which is given as 220 volt, load current is given as 45 ampere, and here the resistance is 44 ohm. So what will be the field current? Field current will be this voltage divided by resistance of the field winding. Field current will be 220 volt divided by 44, this will be 5 ampere. This current is 5 ampere. Load current is 45, field current is 5, so armature current will be 50 ampere. And stray loss is given as 375 watt. What will be the other losses? Armature current flows through the armature resistance, so the heat loss in armature winding will be armature winding. Let's say this is P1, this will be 50 square into 0.01, this will be 25 watt. Next, there will be heat loss in the field winding. P2 will be 5 square into 44, this will be 1100 watt. So these are the two losses, and the third loss is the stray loss, this is 375 watt. So the total losses are 25, 375, 400, 1100. So the total losses are 1500 watt. So the efficiency will be power output divided by output plus losses. The output power will be output voltage into current. 220 P0 will be 220 into 45. This is 9900 watt. So efficiency in percentage will be 9900 divided by 9900 plus 1500 into 100. This is 86.8%. In a salient pole synchronous motor, xt is given as 0.8 pu, xq is given as 0.6 pu, and it is drawing full load current. Since current is full load current, so the armature current will be 1 pu. 1 pu means the rated current or full load current. Power factor is 0.8 leading. Okay, it means the armature current will lead the armature voltage by 36.86 degree, and terminal voltage is also given at, this is given as 1 pu. Then we have to find out the induced voltage. Induced voltage means EF. Okay, so to solve this, let us first draw the circuit diagram of salient pole synchronous motor, and resistance of the machine is negligible. So let's say this is the armature terminal. I am drawing per phase equivalent circuit diagram of synchronous motor, salient type synchronous motor. Here we have terminal voltage of 1 pu. The armature current is, this is also 1 pu at 0.8 leading power factor. Let's say this is xt. So here voltage drop will be JID into XD. This is XQ. So here voltage drop will be JIQ into XQ. This is the representation of salient type synchronous motor. Although the armature current is IA, the voltage drop here will not be JIA into XD. This will be JID into XD. And this voltage is induced voltage EF. Since resistance of the machine is negligible, I have not shown the armature resistance. So what will be the equation? Equation will be Vt is equal to EF plus direct axis voltage drop and quadrature axis, the voltage drop in quadrature axis reactance. So this will be EF plus JIDXT plus JIQXQ. Vt is given, ID is not given, IQ is not given, XD is given and XQ is given. So we have three unknown in this equation. Instead of ID and IQ, we have IA. So we cannot simply find out the value of IF with this equation. So to find out, now let us draw the phasor diagram of salient type synchronous motor. So first in the phasor diagram, we will show the direct axis. Let's say this is the direct axis. This is the direct axis, and let's say this is the direction of EF. Since this is direct axis, so ID will be in this direction. This is D axis, this is Q axis, and since this is the case of motor, let's say the machine rotates in anti-clockwise direction. So the phasor of Vt will lead the phasor of EF. In the final phasor diagram, this will be the direction of EF. So in case of motor, in synchronous machine, we have studied that in case of motor, the phasor of Vt will lead the phasor of EF, while in case of generator, phasor of Vt will lag the phasor of induced voltage. So let's say this is direction of Vt and this is direction of EF. So this is direction of Vt. Now the current is 1 pu and 0.8 leading. The power factor is cos phi is 0.8, so phi will be 36.86 degree and the current will lead the voltage. So the armature current is, let's say this is Ia and this angle will be 36.86 degree. If this is the armature current, the horizontal component will be direct axis current. This is the ID and its vertical component will be IQ. Okay, so now we have the direction of IT. This is the direction of actual direction of IT. Now let us, this is the phasor of EF. Now if in EF we will add JIDXT, then add JIQXQ, we will get VT. So first in EF let us add JIDXT. So this is the direction of ID, then what will be the direction of JID? If you will multiply it with J, this will rotate anti-clockwise by 90 degree. So this is the direction of JID and XT is a scalar. So this is the direction of JIDXT. Okay. And what will be the direction of JIQXQ? The direction of IQ is, this is the direction of IQ. So the direction of JIQ will rotate anti-clockwise by 90 degree. So this is the direction of JIQ into XQ. Now we have to add these two quantities in EF, then we will get the phasor of VT. So let us first add JIQXQ in EF. So in EF we will first add JIQXQ and then JIDXT. JIDXT is in downward direction. This is JIDXT. And after adding that we will get VT. So this phasor will give you VT. This is VT, this is EF. So the angle between VT and EF will be the torque angle delta. Okay, now this angle is delta and this angle is phi. So this total angle will be arithmetic sum of delta and phi. Okay, so what will be ID in terms of IA? ID will be IA sin delta plus phi. From the phasor diagram you can see that this angle is arithmetic sum of delta and phi. Okay, while if the current was lagging, you would find that here you would have the subtraction of delta and phi. Similarly, the quadrature axis current will be IA cos delta plus phi. Okay, so this was about the phasor diagram of salient type synchronous motor for a leading current. Now we have to find out VT, we have to find out EF. So EF will be VT minus JIDXT minus JIQXQ. Again, VT is known, XD is known, XQ is known, ID is not known, IQ is not known. But we have relationship between ID and IA. So can you find out ID with this relation? For finding out ID, IA is known but delta is not known. So we have again an unknown here. So again we cannot use this equation to solve EF. But in theory lecture, what we have studied, if we slightly modify this equation, how we will modify? these are vectors, these are not magnitude of ID. This is the current ID, okay, the phasor of current ID, phasor of current IQ. So let us do some modification as we did in the theory lecture. Vt minus JIDXT minus J. Let us write this IQ is the vector sum of IQ and ID will give you IA. So IQ can be written as the vector IA minus ID. This is IA vector minus ID vector into XQ. Vt minus, let us write first this term, minus JIAXQ minus JIDXT minus minus plus JIDXQ. Or EF will be Vt minus JIAXQ minus JIDXT minus XQ. Okay. Now in this equation, the direction of EF is, in the phasor diagram, this is in upward direction. What will be the direction of this vector? Minus JID, let us write it as plus and minus JIDXT, or let it be minus only. So what is the direction of this vector? The direction of EF is in upward direction. The direction of ID is this, direction of JID is downward. So what will be the direction of minus JID? Minus JID will be in upward direction. Minus JID, and XD minus XQ is, this is always positive because XT is always greater than XQ. The direct axis reactance is always greater than XQ. Okay, so what we find, the direction of this vector is in upward direction. Okay, so what will be the direction of this vector? We have sum of three vectors. Out of these three vectors, two are in upward direction. The two vectors are collinear. So from the property of vector, this will also be in same direction. If three vectors are in same direction, EF can be written as, if three vectors are in same direction, let's say A plus B is equal to C, and if all the vectors are collinear, C can be written as mod of A plus mod of B. So the mod of, or EF can be written as, modulus of C can be written as modulus of A plus modulus of B. Just take the magnitude of these two vectors and add them. So modulus of EF can be written as modulus of Vt minus JIAXQ plus modulus of minus JIDXT minus XQ. This is the way we do the calculation in salient type synchronous machine. Okay, so now let us first find out this vector. After finding out this vector, because in this vector Vt is known, Ia is known, and XQ is also known, so this vector can be found out. The direction of this vector will also be found out. Let's say Vt is reference, this is 0 degree. The clockwise direction will be negative, anti-clockwise direction will be positive. So this is 0 degree, and direction of this vector is in the direction of EF. So first we will find out this vector, and its direction will tell you the direction of EF. So this vector will be in the direction of, okay, so whatever will be the angle of this vector, okay, that angle will give you the value of delta. And once delta is known, you can find out the value of id. Id is equal to ia sine delta plus phi. So let us first find out Vt minus JIaxq. Actually these things are the part of theory lecture. The question is not so lengthy. If you have to solve this question, it is understood that you should already have all these concepts. So just to solve, we should start from this formula only. And before this formula, all these things are the part of theory lecture. Okay, so Vt is 1 pu minus J. Ia is, the magnitude of Ia is 1 pu, and xq is, here we have vector Ia. So Vt is 1 minus J, and what is vector Ia? The magnitude of Ia is 1, and if Vt is reference, Ia is in anti-clockwise direction, so Ia will be 1 angle 36.86. So this is 1 angle 36.86 into xq. xq is 0.6. This will be 1 minus, what is angle of J? Angle of J is 90 degree. So this 90 degree will be added to 36.86, and 1 will be multiplied with 0.6. So we have 0.6 angle 90 plus this 126.86 degree. Okay, so this is the value of Vt minus JIaxq. If you will solve it, we will get, this will be 1.44 angle minus 19.44 degree. Angle is minus, it means the direction of this vector or the direction of EF will be clockwise to the reference. Okay, negative sign here represent that this vector will be to the clockwise of the reference. Okay, so it is already in clockwise direction, and delta is 19.44 degree. Okay, and its magnitude is 1.44. Now we have to find out magnitude of this quantity. So let us first find id. Id is equal to ia sine delta plus phi. Ia is 1. Ia is 1 sine delta is 19.44 and phi is 36.86. This is 0.8319. This is the value of id. Okay, so what will be this? The magnitude of this quantity will be 0.8319 into xt minus xq is, xt is 0.8 and this is 0.6, so this is 0.2. So the modulus of EF will be 1.44 plus this quantity. This will give you 1.606, and angle is already 19.44. Since it is in clockwise direction to the reference, this will be minus 19.44 degree. Okay, so angle of this vector only, this will give you the delta. You need not to calculate the value of, exact value of EF vector to find out delta. From this vector you will get delta, then you will calculate id, then you will calculate the complete value of EF. We have a distribution transformer whose kVA rating is 22 kVA, voltage is 220 volt. The voltage rating is 220 volt, 200 by 220 volt. This is the voltage ratio and 50 Hz. So Let's say this is the 2-winding transformer. The voltage ratio is 2200 by 220, and it has to be connected as an auto transformer so as to get 2420 volt output voltage, and kVA rating has to be maximum. So this is the voltage rating. This is the voltage rating of the, this is the primary voltage rating, this is secondary or the voltage rating of low voltage side. Now let us find out the current rating of these two windings. This is 22 kVA transformer. So current rating of this winding will be 22,000, the kVA rating divided by voltage rating of high voltage side. So the rating of this winding is, current rating of this winding is 10 ampere. It means in any case, whether it is working as 2-winding transformer or it is working as an auto transformer, this high voltage winding cannot sustain a current more than 10 ampere. This is the meaning of current rating of this winding. Similarly, what is the current rating of this winding? Same kVA divided by voltage is 220 volt. This is 100 ampere. So current rating of this winding is 100 ampere. Okay, and from the turn ratio it is also obvious that when this winding will carry, then when high voltage winding will carry 10 ampere, at the same time low voltage winding will carry 100 ampere. These two windings are magnetically coupled with core, and let's say this is the dot polarity. Now this 2-winding transformer has to be connected as an auto transformer so as to get the output voltage 2420 volt. Okay. Basically, how you will get 2420 volt? This is 2200. If you will add this voltage to 220 volt, you will get the desired output voltage. So we have to make the connection such that the output voltage will be summation of these two voltages. Okay, and if this is the dot polarity, it means when this terminal will be positive, at the same time this terminal will be positive. Let's say this is A, this is B, this is C, and this is D. Now in the output we have to get summation of these two voltages. These are two voltage sources. The windings can be thought of a voltage sources, and you have to get summation of these two voltage. So let's say you have two voltage source. How you will get summation of these two voltages? This is 2200, this is 220. To get the summation, what we need to do, we have to connect the negative terminal of first source to the positive terminal of second source, and at the remaining terminal you will get voltage which will be summation of these two voltages. If you will check it, let's say this is the output voltage. Here you will have a gain of V0, here you will have a drop of 2200. Now move, again you will have drop. Okay, so V0 will be 2420. So to get the summation, what we need to do, we need to connect negative terminal of first voltage source to the positive terminal of other voltage source. Okay, so the terminal A will be connected to terminal D, or negative of this has to be connected to positive of other. So we can get this much voltage by two ways, either by connecting A to D or by connecting B to C. So let us connect B and C. So for connecting B and C, let us shift this part first downward, okay, then connect here. This is the dot polarity. Shift it here. This is A, this is B. Okay, then C will be connected to B. This is C, this is D. This is dot, and dot is at C. So here we will have dot, and this will be the output voltage. The positive and negative are connected. Here you have positive, negative, positive, negative. So positive and negative are connected, and at the remaining terminals you will get 24, 20 volt. This is output terminal. Now to get the kVA rating of this auto transformer, the kVA rating will be, kVA rating is voltage rating into current rating, the maximum voltage that this transformer can sustain into the maximum current that windings can sustain. So when you will apply maximum voltage to 2200 here the voltage difference will be 220, because these two windings are coupled. In the two winding transformer you have only magnetic coupling of windings. In the auto transformer, with the magnetic coupling or along with the magnetic coupling, you have electrical connection between the windings. So if you will apply 2200 here, due to magnetic coupling you will have 220 volt generated across this winding. Okay, so you have given maximum voltage, here also you have maximum voltage. Now if you will add these two voltages, here you will have a gain of 220, here you have gain of 2200, so this output voltage will be 2420. So the voltage rating of auto transformer is 2420. And what will be the maximum current in the load? Let us connect a load here. Okay, so the current rating of the load, this will be limited by the current rating of winding. So let us assume the maximum current is flowing in this winding. This is 10 ampere. According to dot convention, if a current is entering into the first dot, in the secondary winding the current will leave from the dot. Okay, so if 10 ampere is entering here, 100 ampere will leave from this dot. 10 ampere is entering into the dot, so in the low voltage winding 100 ampere will leave from the load. Okay, this is the input terminal. So let us connect a source at input terminal. This is source, this is load. Okay, so 100 ampere, if 100 ampere will flow through this winding, here also current will be 100 ampere. Okay, and this 100 ampere is the maximum current corresponding to the rating of winding. So the output kVA will be the output voltage into output current. Okay, so this will be 242,000 volt ampere or 242 kVA. If you have to find out kVA rating of a transformer, if you assume lossless transformer, the kVA can be found out from output side as well as input side, because on the two side kVA will be same. Let us verify it. What is this voltage? The voltage across this source is 2200, and what will be this current? This current will not be 10 ampere. 10 ampere is the current entering into the high voltage winding. Okay, here the current is 10 ampere and 100 ampere current is leaving from this dot. So if you will apply KCL here, this is the third path, and here the current will be 10 plus 100. This is 110 ampere. Okay, So what is the kVA supplied by this source? kVA supplied by this source will be source voltage into current from this source. Current from this source is 110 ampere. Okay, so again you will get 11 into 22, this will be 242 volt ampere, that is 242 kVA. For finding out in the question it is asked that the maximum possible kVA of this auto transformer when the output voltage is 2420 volt. Question is asked about the maximum possible kVA for output voltage of 2420 volt. So from the statement or from the question, it seems that there may be one more kVA rating for this voltage. If for this voltage, output voltage, maximum kVA is asked, so there may be some more kVA for the same output voltage. Okay, so let us try to find out whether there will be more than there may be another rating of this auto transformer for the same output voltage. So to find out other rating, in this case, in the previous case, what I have assumed, the output voltage is 2420 volt. Okay, this will be fixed. Now instead of connecting input between terminal A and B, this is also possible that input will be given between B and D. Let us not connect source here. This is terminal A, and let us connect a source between B and C are connected. This is B and this is D. Let us connect a source here. Okay, in this case also the maximum voltage will be, or the voltage rating will be 2420, because this is 220 volt winding, so maximum source voltage that you can apply is 220 volt, otherwise the code will saturate. So if this voltage is 220 volt, these two windings are magnetically coupled and this is high voltage winding, so according to turn ratio this voltage will be 2200. Now if you will apply KVL here you have gain, here also you have gain, so these two voltages will be added and in the output you will get 2420 volt. Okay, so you got the same output voltage even if I changed the input terminal. Now let us try to find out kVA rating of this transformer. So for kVA rating, what we will do, we will give the maximum current to any of these two windings. Let us again, the maximum current 10 ampere is flowing through this winding. So if 10 ampere is flowing, entering into the dot, 100 ampere will leave from the dot, or for better reference, we have a tendency that we have an habit that current flows into the load. So let's say current will flow in this direction. So let's say current is flowing, 10 ampere current is flowing out of this dot. Okay, so if current is flowing out of this dot, in the low voltage winding current will enter into the dot. If the current is 10 ampere here, so in the low voltage winding 100 ampere current will enter here. Okay, so if 10 ampere current is here, there is no branching, so in the load current will be 10 ampere. So what is the output kVA? Output voltage 2420 into current is 10 ampere, while in the previous case current was 100 ampere. So here the kVA rating will be 24.2 kVA, the output kVA, and input kVA will also be the same. Let us find out that. Here current is 10 ampere and this current is 100 ampere, and this current is 10 ampere, so the total current will be 110. So input kVA will be 220 into 110. Okay. This will be 24.2 kVA. Okay. So for same output voltage 2420 volt, one possible kVA is 24.2 kVA and other possible kVA is 242 kVA. We got this kVA when input terminal is across high voltage winding, and we got this kVA when input is across low voltage winding. And question is asked about the maximum kVA, so answer will be 242 kVA.